Hello Doctor and everyone, we are Group 9 and it consists of myself, Atinia and Adriana and also Ezandra, and our project is titled Rehabilitation Pulley System for Shoulder Therapy. This study explores how traditional pulley system, while useful, can be improved by integrating adjustable resistance, motion control and ergonomic features. So our goal is to design a safer and more effective system tailored to patient recovery needs by using principles from dynamics and biomechanics to guide our analysis.
Shoulder mobility is something we don't always think about until we lose it. Simple tasks like reaching for a shelf or putting on a shirt suddenly become difficult when the shoulder is injured or recovering from surgery. The shoulder joint is one of the most complex in the body, especially the glenohumeral and also acromyoclavicular joints. When these joints are affected, motion, strength, and even our sense of body awareness, or what we can call as proprioception, can become impaired. This often leads to stiffness, poor posture, and unfortunately a higher risk of re-injury if not treated properly. That's where rehabilitation pulley systems come in. This system guides the patient through gentle, controlled arm movements that helps to slowly restore range of motion and muscle strength without overwhelming the joint. They are simple, affordable, and commonly used in clinics and at home. But despite their benefits, traditional pulley systems do have limitations. They often lack of adjustable resistance, don't provide real-time feedback, and can't adapt to individual recovering progress. Without these features, recovery may not be as efficient or as safe as it could be. The goal of rehabilitation isn't just about movement, but it's smart, supported movement that rebuilds function and confidence. That's why there's a growing need to improve these devices with better design and responsiveness. Traditional shoulder rehabilitation pulley systems have been around for decades, and while they offer basic support, they are far from perfect. One of the main issues is the lack of adjustable resistance. This can lead to inconsistent muscle activation, especially in early recovery when control and precision matter most. Secondly, therapists also face limited control over the movement as it relies heavily on the patient's own effort, which may not always be accurate, safe, or effective. Most of these systems use a fixed mechanical setup that offers little flexibility, which means they can't adapt to different recovery stages or individual needs. And perhaps most critically, without proper resistance control, patients are exposed to sudden force spikes, which may increase the risk of discomfort or even re-injury. So, it is clear that there is a need for smarter, safer, and more adaptable tools that can support recovery while minimizing the risk.
Let's now move on to the hypothesis for our project. So we hypothesized that by integrating adjustable resistance, guided motion control, and ergonomic design into the traditional pulley system, the overall rehabilitation process can be significantly improved. These improvements are expected to enhance three main aspects, which is safety, comfort, and the effectiveness of physiotherapy session. More specifically, the enhanced system is expected to bring the following advantages. Firstly, it is expected to reduce overexertion and prevent incorrect joint movement. Secondly, it aims to be safer for post-operative patients or individuals with low muscle strength. Thirdly, the system is designed to support personalized and controlled exercises. In addition, we expect it to lead to more consistent rehabilitation outcomes. Moreover, the improved comfort and ease of use are likely to increase patient adherence to therapy. And finally, with all these improvements combined, the system is anticipated to promote faster functional recovery compared to traditional pulley system.
Now, I will explain the methodology used in this research. This study adopts a theoretical and mathematical approach grounded in fundamental dynamics principles. Since no physical testing or equipment was used, the analysis is entirely based on mechanical modeling and simulation. We first conducted a review of existing rehabilitation pulley systems to understand their structure, clinical usage, and limitations. From there, we focused on three main factors: the resistance mechanism used in the system, the typical motion paths patients follow during therapy, and the overall therapeutic goals and safety concerns. The main objective of this study are to identify risks and inefficiencies in current designs and propose improvements that enhance safety for the patient, motion efficiency during rehabilitation, and therapeutic effectiveness over time. Now, to understand how the Pulley systems behave, we apply 4 key dynamics concepts. First, rectilinear and curvilinear kinematics were used to analyze how the pulley rope moves vertically and how the shoulder moves in an arc. This helps us calculate displacement, velocity, and joint stress. Second, we apply absolute dependent motion to model how the healthy arm controls the movement of the injured arm and to ensure symmetrical and safe motion transfer. Third, using the work and energy principle, we calculate the effort required by the healthy arm and evaluate how effective the system is at providing proper resistance. And finally, we consider conservative forces and potential energy to track energy transformation and identify risks from sudden energy changes that could lead to injury. Now, let's look at the first part of the results, the resistance applied by 2 types of pulley system, traditional and controlled resistance. In a traditional pulley, the force needed to lift the injured arm comes from the patient's healthy arm. This force included both gravity and inertia, and it varies with how fast the patient pulls. For example, at a slow speed, the required force is about 29.4 Newton, but at a faster speed, it increases to 32.4 Newton. This creates a variation of 3 to 4 Newton, which affects muscle activation and makes the therapy inconsistent. The work done remains constant at around 14.7 joules, but the problem is lack of control. In contrast, the controlled resistance system using a spring mechanism produces a consistent force of about 18 Newton regardless of speed. The work done here is only 2.7 joules, which is gentler and safer, especially during early stages of rehab. It can also be adjusted over time to suit different rehab needs. This table summarizes the key comparison. Traditional systems rely heavily on manual effort and vary in force, while spring-loaded systems are consistent, safe, and adjustable. Let's now connect this to how dynamics principles help us understand and improve this system. Using rectilinear kinematics, we model how the rope moves vertically. This gives us clear values for position, velocity, and acceleration. With curvilinear kinematics, we analyze how the arm rotates about the shoulder and identify where stress may build up. Through dependent motion, we can see that a sudden movement by the healthy arm directly affects the injured arm. This highlights the need for motion symmetry and control. Using weight energy analysis, we can quantify how much effort is required and compare the energy demands of traditional and controlled systems. Finally, potential energy calculations help us design safe pulley heights and resistance settings that suit different stages of therapy. This brings us to the final section, how resistance and dynamics principles are closely linked. In traditional systems, unregulated acceleration can lead to force spikes and potential injury. The 1:1 motion ratio from dependent motion means any sudden force is directly transferred to the injured arm. There is no control over energy input, making it difficult to match the therapy to patient strength. The gravitational resistance is fixed about 14.72 joule, which can be too much or too little depending on the patient. In contrast, spring-based systems allow for smooth regulated motion, enable motion dampening to protect the injured arm, provide adjustable resistance so therapy can be personalized, store lower, safer levels of potential energy. For example, only 2.7 joule with a 60 Newton per meter spring stretched by 0.3 meter.
As for discussion, shoulder rehabilitation demands not just about movement, but controlled intentional movement. Traditional pulley systems, though commonly used, often fall short in delivering the precision that recovery truly needs. One major concern is the inconsistency in applied force. Since these systems rely on the patient's uninjured arm to lift the injured one, any variation in pulling speed directly affects the load. A sudden or fast pull can generate up to 1.5 joules of energy compared to just 0.17 joules during slower, steadier movement. This sharp spike in force places unnecessary strain on healing tissues, increasing the risk of re-injury, especially during the early stages of recovery. Another limitation lies in the lack of motion isolation. Traditional systems create a 1:1 movement ratio between both arms, meaning the injured shoulder mirrors the motion of the healthy arm without any resistance dampening. This often results in jerky, uncontrolled motion which can destabilize the joint and hinder safe muscle activation. In contrast, spring-based pulley systems provide a more advanced, patient-friendly solution. This system integrates built-in adjustable resistance, which allows the therapist to customize the force to match each stage of recovery. For instance, using a spring with a stiffness of 60 nano per meter stretched to 0.3 meters delivers a consistent 18 newtons of force, equivalent to 2.7 joules of controlled energy. Unlike gravity-based systems, this force remains stable regardless of movement speed, which greatly enhances safety and reliability. More importantly, spring-based mechanisms allow for gradual resistance progression, which is essential in structured rehab programs. Early-stage patients, such as elderly individuals or those recovering from surgery, can begin with lighter resistance and increase it as strength improves, minimizing both overexertion and undertraining. In short, spring-based pulley systems do more than assist motion. They support recovery in a way that's measurable, adaptable, and significantly safer. They allow patients to rebuild mobility with confidence, while giving therapists better control over the rehabilitation process.
To conclude, this comparison highlights the differences between the traditional pulley and the enhanced spring-based pulley system across 6 aspects. Let's begin with resistance. Traditional pulley rely on fixed resistance through gravity, while the spring-based pulley provide adjustable resistance. This flexibility directly improves the suitability for recovery, as the resistance level can be tailored to match the patient's stage and physical capability, making therapy more effective and patient-specific. Next, looking at force, traditional systems produce force that varies with speed, which can lead to unpredictable movement. In contrast, the spring-based pulley delivers a consistent and controlled force. This has a direct impact on energy management, as the controlled force helps regulate energy transfer and avoid sudden spike and reducing unnecessary strain on the body. Lastly, consider safety. Traditional pulley pose a risk of jerky motion, which may cause discomfort or even injury. The spring-based pulley is safer and more controlled. This improved safety contributes to better clinical usefulness, making the device more reliable, consistent, and suitable for structured rehab sessions, and also long-term therapeutic use. Overall, this improvement demonstrates how the enhanced design not only addresses mechanical limitation, but also leads to better outcome in recovery, energy efficiency, and clinical effectiveness.